Hello, how are you doing, Glory? You're
I'm
good. Glad to see you
fine.
here. Still enjoying class?
Yes, sir.
Yes, sir.
Oh, good. Very good. So I am going to go ahead and I'll wait just a minute and get started. Any updates from your lives? Anything interesting going on?
Yeah, Prof. Manager was chatting with one of my ex from Africa University who is in Malawi, and he was giving me some updates of they are doing some local kind of climate change control project. So
Oh,
it's still
really?
at the primary stage. Yes, it's still at the primary stage. I said, that was good to keep updates with him and then to know what they are doing. They're trying to locally harvest the CO2 and see how
Uh-huh.
they can control the emission of the CO2 in the environment. So it's just like
Um, can you find out more specifics and then write it up in an email and send it to me? This might be something that we could incorporate into your project, possibly,
okay.
over the 2 years and stuff. And maybe there's a way to get involved. I really like to see people get involved locally with their projects when it comes time for that. So,
Mhm.
yeah, find out more, send me some info about it, maybe even some contact info, and, we can chat about what could be possible next steps. If you're
Okay.
interested, let's find out about what it
Yes,
is and
yes,
see if it fits.
it's okay, Prof. I'll do that.
Okay. Let's see. So I see that Caldrian has done the peer teaching on climate classifications, but I don't see that anybody else has. So I'm going to post in the link to the flip. Um, that's in the chat. I'll also send it out with the next email when I give the email that's got the link for the latest video. But if you can do that over this weekend, that would be great. Because on Monday, I'd like to get everything graded. We have to have our midterm grades in by Tuesday. So that's going to factor into it. I also posted a uh, quiz or a little exam up on like a midterm exam. It's got like about 35 questions. It's not too difficult. I just want to see how good you guys are at responding to these questions. Um, in terms of the overall points, it's not a ton. I like to have most of the points in the class coming from the pure teachings because that it's really a good way for me to tell what you know and what you don't know. But give it a shot, and let me know if you had any problems with any of the questions. It's my first time trying to do an online kind of exam, for this class. And so I just want to see how it works out. It's like a little test run, if you will. I mean, there will be a final at the end of the course, but think of this as just a small test run. Um, okay, with that said, I'm going to go ahead and get started. Let's see. And here we go. So we are moving on. Um, have most of you been reading the book? Has that been has everybody been doing that?
Yes, sir.
Okay, good. Because we should be in chapter 8 now. You should be getting to chapter 8. I heavily suggest reading along with the textbook. It has more information than I'm able to go into in these short little lectures. And I think hopefully it's well written. So we're going to get into IPAT model and climate prediction. Um, so first off, I always like to go over where we are. Um, we've discussed that adding an infrared absorbing gas will warm the climate. We talked about that in chapter 4. In chapter 5, we talked about how we are adding infrared absorbing gases to the atmosphere. And based on this, you would predict that the climate should warm. We talked about that in chapter 6 when we talked about transient warming and radiative forcing, etc. In chapter 2, we observed that indeed we are seeing warming on the planet. We know this from the surface thermometer record, as well as satellite data and all sorts of stuff. So we know that we are warming. And from what we covered in chapter 7, we talked about all of the other possible ways to attribute why we're seeing this warming. We've seen that it's most likely attributable to greenhouse gases, specifically CO2 amounts. Okay, and that's all well and good. So I think we've made the case for the theoretical basis why adding these gases would cause warming. I think we've shown that we are adding the gases and we are indeed seeing warming, and there probably isn't any other credible explanation for why we're seeing it so fast. But that's all about the past, right? We really want to know most about the future, right? And so that, that leads us to our favorite equation, this equation up here, right? And this tells us that the climate is really determined by 3 factors, right? We've got the solar constant, which is the amount of energy hitting the planet from the sun. We have the albedo, which is the amount that's reflected away before it gets a chance to warm the planet or anything else. And then for that which isn't reflected away, it's absorbed in the planet heats up. It acts as a black body and then radiates energy outwards in the form of infrared. And so we know if we have an infrared absorbing gas in the atmosphere, that acts as a layer which reflects additional energy back to the ground and heats up the surface more. And so that's kind of what determines our climate. We know that in the end, energy out leaving the planet from the upper atmosphere has to equal the amount of energy coming into the planet. And it may take some time for the planet's temperature to adjust. And so our primary driver for future climate change, as we talked about, as well as the driver for current climate change, is this addition of greenhouse gases, specifically carbon dioxide. And we've talked about how that's basically increasing this N constant, the number of layers, right? And so to predict the future of climate change, we need to know how this number N, the number of layers, is going to change. And since greenhouse gas release is a product of human activity, specifically human economic activity, we really kind of need to be able to predict human activity, or at least quantify it as it relates to emissions of these greenhouse gases. And this is what a lot of climate scientists do. It's a significant part of the IPCC report. And it really gives us an idea of what can we do to change things, where we should kind of aim our sights, if you will, on trying to change these emissions so we can positively affect global warming. And so we got to look at what factors control emissions. And this is discussed a lot in the book. And we're going to come at this from the same angle that they come at it at the IPCC. And the first main factor is going to be population, just the sheer number of people on the planet. Okay. At the moment, make the calculations and take an average. The average person on the planet emits probably about 5 tons, or is responsible for about 5 tons of CO2 emissions per year. That's a fairly large amount, right? And so one would expect the more people we have, it would mean we have more emissions if we stayed at the current rate of 5 tons of CO2 emissions per year, right? And so any kind of prediction of what future emissions are going to look like are really going to have to take into account population. So give me some examples as to where this 5 ton of CO2 footprint comes from you in your life. And why don't we start with you, Glory? Since you were talking about CO2 emissions, what is it that you do that creates CO2 emissions? You're on mute. You're still on mute. You're gonna have to unmute yourself.
Okay, the setting of firewood, setting fire on firewood for cooking, local cooking, yeah.
Sure. What else?
And the use of setting of bush also on fire.
Okay.
Bush burning.
Okay.
For agricultural purpose.
What about right at this moment? What are you doing right at this moment?
Studying.
You're studying. How are you studying? How are you participating in this class?
Okay, the air I'm breathing out, yes.
Well, right, but we're talking about emissions beyond respiration. So what are you currently using to talk with me? Are you on a laptop or a phone?
I'm on a phone, yes.
Okay. And does the phone run on solar energy? Where did you get the energy to power up the phone? You plugged it in somewhere?
In the electricity.
Right. And so big question is, where does that electricity come from? And how much CO2 is used in creation of that electricity? Here in the US, a large portion of our electricity is made from coal-fired plants, which emit a ton of CO2. Desire, what about you? What things do you do that add to your carbon footprint?
So the beginning is respiration. I respire, so I take out carbon dioxide, and then I use appliances, starting with the phone as well as the device I'm on. So powering lights and everything, I add, yeah, that's how I add carbon dioxide into the atmosphere. Basically that.
Okay, so I would argue that your respiration doesn't count. The reason why it doesn't count is what you're respiring on is on the food that you ate, specifically the sugars that you imbibe, that are giving you energy and fueling glycolysis and all that. That came from a plant which had to take that carbon out of the atmosphere. So really the net amount of emissions kind of equal in that. Okay. Caldrian, how about you? What's your carbon footprint like? Where does that come from?
Just day-to-day travel. And I didn't, well, I wasn't knowledgeable of the phone actually emitting carbon, well, CO2. I wasn't aware of that. So definitely that. At this point, I'm on a laptop, so of course, being on a laptop, um, traveling every day. Um, um, what else would consist of a carbon footprint that comes to mind?
Do you turn on the lights in your house?
Mm. Well, that's
So to be clear on the phone thing, it's not that the phone emits CO2. It's that in order to power your phone, you had to plug it in, which is electricity. A lot of the stuff we have uses electricity. And how do we generate that electricity is a key driver of CO2 emissions. Most of the CO2 emissions are coming from energy production. We use energy for everything. Abood, what are your thoughts? Your carbon footprint?
Actually, I will say that there are many ways that we release CO2 to the environment, especially when we are traveling and using vehicles. That fuel, when there is no complete combustion of that, there's a lot of release of CO2 to the environment. And also, as I've said on the hydro electric power generation, they use a lot of fuel in producing that.
That's great. That's great. So this is going to lead into the other two things that we really need to talk about in order to talk about, future climate change. Okay. So we've talked about the number of people. People use stuff and they do stuff, right? Now it's going to be different depending on which people you're talking about. So one of the other factors that they've divided, and there's a lot of different ways you could divide this, but this is a really interesting way to divide it, is affluence per person. This is basically about how rich people are. And why are we talking about how rich people are? Well, the more rich you are, the more you're going to consume stuff, right? So not everybody can afford an iPhone, right? But those people that do get the latest and greatest iPhones. Not everybody can afford a computer, but those that do have computers around the house. The richer you are, very rich people may have several televisions in their house. They've got lights automated to go on and off. And so the more rich folks are, the more they tend to consume. And just about everything we have in everything we do requires energy. And so the more you can do stuff, the more you're going to consume. And we measure this consumption by a factor known as gross domestic product. Sorry, that's on there. Gross domestic product, also known as GDP. That's the total value of goods and services produced. And so the world average gross domestic product, if you just took all the GDP of the world and divide it by every person, is about $11,000 per person. In the US, it's actually closer to about $60,000 a person. And in some of the poorest countries, it's actually less than $1,000 per person. I mean, if you think about that, that's pretty intense because we're talking about like $3 a day in terms of how much folks are spending. So a lot of us in the positions we're in, the fact that we can even participate in this course means we're lucky enough to not be, at the very bottom in that. And so we have population, which is how many people there are. We know people use stuff. The more stuff that you use is going to affect our emissions. And so then the last part is going to be on the technology that's used to generate energy, right? So as Abood mentioned, you could have hydroelectric power. Hydroelectric power doesn't do CO2 emissions, right? That's great. But it turns out, there are other types of energy production that do emit a lot of energy. And so we really have to look at how efficiently the economy is utilizing this temperature or utilizing this technology, right? And is the technology that they're utilizing, is it generating a lot of CO2 or is it not? And what's nice about these, using these three kind of factors, is we can put metrics on them, right? For population, we have number of people. For affluence per person, we have total GDP per person. And then finally, for the technology, since we're talking about, these goods and services that are being provided, it takes energy to provide them, whether it's the energy that is going into the electricity generation to power the phones, or if it's energy that, you need to consume to drive a truck to get to your job. If you're a delivery person, it's driving the truck and the course of the job, etc. So we look at, for technology, our units is the amount of CO2 emitted per that dollar of GDP. Okay, and this gives us what we call the IPAT relationship. Okay, where the impact equals the population times the affluence times the technology. This is the most common thing that folks use when they're talking about trying to predict how society is going to produce more CO2 or less, or how it's going to change. Okay. And so in IPAT, we have metrics. Our population is going to be measured by the number of people. Our affluence is going to be measured by the amount of GDP per person, total dollars of GDP per person. And then the technology is going to be measured by the amount of CO2 emitted per dollar of GDP. And if you look at this carefully, if you look at the units, you can see that the number of people that cancels out, right? And then you can also see that the amount of GDP that cancels out. And so the units we're going to be left with is the amount of CO2 emitted. And that's really what the IPAT is really about, is it gives us the amount of CO2 we expect based on the number of people, their affluence, and the technology they're using to power their affluence. Does that make sense so far? Desire, I see you're shaking your head. This is crazy.
Not really. I don't get the canceling out there. Could you please go one more time?
Oh, sure. So since affluence is our units is the amount of GDP per person, like we were talking about, what's the average GDP per person before? I think it's 11,000. Could be 60,000 in the US, could be 1,000 in poor countries. It varies depending on where you are in a country and which country you're in. But that's dollar amount of GDP per person. So the number of people is going to cancel out. When you multiply these together, if I've got 10 people at $5 per person and I multiply those out, I'm going to get $50, but my units will no longer have people in it, right? Because it's 5 people times $10 a person, $50. Okay. Same thing here. When you multiply all of this out, we have dollars of GDP in the numerator here and dollars of GDP in the denominator over here. We're multiplying these out, so the dollar figures will get canceled. And so the only units we'll have left really is the CO2, because our technology term is how much CO2 is emitted per dollar of GDP, right? So if we have $50 of GDP, then, and we multiply this, say it was, 1 gigaton per dollar of GDP, then it would be 5 times 1, or 5 gigatons total. And so this equation, the I is the impact. That's our emissions. The impact is the amount of emissions. Now, this one is the one that had been used for several years. But in more recent years, we've started to unpack this technology term. And this technology term, if we look at the units here, remember, this is how much CO2 we emit per dollar of GDP. So what we're going to do here is we're going to split this term up. We're going to split it into 2 terms, which is the energy intensity and the carbon intensity. Okay, these two terms. So our energy intensity is going to be the joules of energy per dollar of GDP. Okay. So how much energy are we getting for each dollar of GDP? And then the second term, our carbon intensity, is how much CO2 are we getting per that joule of energy? So this gets at how we dissect if you're doing hydroelectric power versus a coal-fired plant, or burning gasoline, or using solar power, right? Obviously, if we changed our means that we're making the energy. So if we went from burning fossil fuels to using solar energy, we would expect the emissions to go down. That's because for every unit of energy that we're making, if we're doing solar power, we're not emitting CO2. But if we're burning fossil fuels, we're emitting a lot of CO2. And so that's our carbon intensity. The other thing that could change is maybe we use less energy. So if we make more efficient iPhones where the battery lasts longer, or we make more efficient light bulbs that don't need as many joules of energy to power that light bulb for a specific period of time, then we'll also emit less CO2. So just imagine we stayed with the same coal-fired plants that are emitting CO2, but now we reduced our energy consumption. So for every unit of GDP, we brought down that energy, so we're using half as much. We wouldn't need to burn as much in our coal-fired plants, and so we wouldn't have as much CO2 emitted. And so that's why we're breaking this apart. Remember, our original term that fit in our IPAT was the CO2 emitted per dollar of GDP. And we know that we're emitting the CO2 in the form of energy production. That's all the things that we listed, whether it was driving your car to work, or flipping on a light switch, or using your iPhone, or heating up water by burning up some wood on a wood-fired stove. It's all about getting the energy to do stuff, to produce and to live. And that's our GDP. Okay. And so rather than just talk about CO2 per dollar of GDP, we break that apart into how much energy per GDP, and how good is that energy at not burning CO2 or emitting CO2. And so we have these two terms. Now, you'll notice that when you multiply these two terms together, joules of energy cancel out up here, joules of energy cancel out down there. So these go away, and you're left with CO2 emitted per dollar of GDP, which is what our term was before, right? So it's okay to break this apart because we're still left with the right units. And, again, this is how efficiently the energy is used. And this is the technology that's used to generate the energy, because both of those can have a significant impact on what our future emissions are going to be. If we can be more energy efficient, and if we can switch to technologies which don't emit as much CO2. And so when we put all these things together, we had this original that IPAT relationship. When we put them all together, the amount of CO2 is going to be equal to the number of people times the GDP per person. This is looking at our economic activity, because remember, all of our CO2 is being generated out of this economic activity. And so then this is how efficiently the energy is being used, how many joules of energy you need for a dollar GDP, times how much CO2 is emitted for every one of those joules. And so again, if you multiply all of these out, people cancel, dollars of GDP cancel, joules of energy cancel, and so you're left with the amount of CO2, which is what we're trying to calculate. So estimating future climate change requires us to estimate how much greenhouse gases we're going to release in the future. So we have to be able to estimate greenhouse gas production in the future. And that's the whole role of this IPAT relationship. Okay, remember, impact equals population times affluence times technology. And we break up this technology term into energy intensity and carbon intensity. So let's take a look at this carbon intensity. So, I've put up here a couple, not all of the different ways that we get energy. Coal is our largest, most carbon intensive form of getting energy. That's about to about 90 grams per megajoule. Oil is a little bit less than that, about 25% less than that, and about 70. Natural gas is about almost half of what coal is in terms of how much carbon it releases. Wind, however, and solar and nuclear, all of those have zero emissions. So obviously, if we can switch from coal to wind or oil to solar or any of these things, increase our or decrease our emissions, that would be great. So let's see how well this way of looking at the world works. Okay. So if we look at between now and the 1960s, for example, we get this little plot. Okay. Your 1960, we had about 3 billion. Okay. And now we have a lot more than that. So our population, it's it's a little bit more than double. It's about 2.5 times where we were at before. So over the since the 1960s, we've seen about a 2.5 times increase in our population. Okay, if you look at affluence, here's our affluence in 1960, and so this is GDP relative to 1960. So we're looking at the GDP now and dividing it by the 1960 numbers. So if they were equal, it would be the value would be 1. So 1960 is our reference period. And you can see the amount of GDP since the 1960s has gone from 1 to about 3 times that value. Okay, so right now we have 2.5 times as many people, and each person is consuming about 3 times the amount of goods and services. So you can already see where this is going, how it's going to be increasing. Now, if we look at energy intensity, okay, energy intensity has actually gone down. So that means that there's just been a general increase in the efficiency of things. Our computers need less energy than they did before. Our batteries last longer. They need less energy than they did before. We're moving to light bulbs that are more energy efficient. And this trend has been going on, increasing the efficiency of many of these different processes for a long time now. And for good reason, there's profit motive. If there's a company that's, is doing some kind of production, whether it's steel production, making cars, whatever, they pay a certain price for the electricity to keep their lights on and to run their machinery. They will pay less if they can make it more efficient. And so they have strong cost drivers to try and buy more efficient lighting, more efficient process of manufacturing their steel or creating their car. We've also seen a large shift from heavy manufacturing to more of service economy. There's fewer big manufacturing jobs, and more service jobs. And so what we see basically since 1960 is about a decrease by about 50%. Our energy intensity has come down by about 50% since 1960, which is great, right? That's awesome. What about carbon intensity? So if we look at carbon intensity since 1960, we see that there was actually a nice steady decrease up until about 1990. We were decreasing the amount of carbon that we're using to generate our energy. So this means, more windmills, more solar power, more hydroelectric power, more nuclear power. That's been a big thing since the 60s. Throughout the 70s and 80s, there was a big jump in nuclear power throughout the world. But then you notice that decrease starts to level off and actually starts to increase. And we're starting to increase our net carbon intensity. And a lot of this is due to China and India, both because their economy is growing and their population is growing and their affluence is growing. And it's mainly driven by this affluence. People need energy to run their stuff. They're buying more stuff. And so they want to power their stuff. And so there's a quick need for energy. And so both in China and India, they're building a lot of coal-fired plants. And so CO2 production has started to go up a lot in those countries because they're turning to coal production again. And so if we take all these together, if we look at what all our factors are, we have a 2.5 time increase in the population since 1960. We have a 3x increase in the GDP per person. People are getting more affluent, there's more stuff to buy, etc. The energy intensity has gone down by about 50%, so that's times 0.5, right? Because things are being made that are more energy efficient. And our carbon intensity has come down a little bit. We're at about 85%, maybe a little bit less, depending on how you read this graph, and our carbon intensity decrease. And so if we pull out our equation, our IPAT equation, right, this equation here, we've got a 2.5 increase in the number of people, 3-time increase in the GDP per person. Our energy intensity has gone down by about 50%, and our carbon intensity has gone down by about 15%. So that's multiplied by 0.85. And so when you multiply all these together, we get the amount of CO2 emitted should be about a little over 3 times what we saw in 1960. This is going to give us a good measure as to, does this IPAT system really work, right, for predicting, human impacts over, like, say, the last 60 years. And so let's go ahead and look at carbon dioxide emissions over the last 60 years. Let me bring that up here. So here's a graph of CO2 emissions. We know it's been going up. And so this is just since 1960. And so we've gone from about 15 gigatons of CO2 per year up to about, maybe this is 45 here, close to it. And so it's definitely gone up. How much has it gone up? That's about a 3-time increase. So what did we say in our calculation? 3.18. And here we're seeing about a threefold increase in our CO2 emissions since 1960. And this is mainly due to where the population increased, the affluence increased, but those were offset by decreases in the energy intensity and the carbon intensity. So your thoughts on this? Are you surprised that it Do you get, first off, how we're making the calculation, how we're dividing it up into these 4 categories, and how we're trying to make this calculation, this prediction of carbon dioxide emissions?
Yes, sir. The graph here isn't really surprising, because it just correlates with of course, the increased CO2 emissions, which will in turn lead to a change in climate.
Right. So it matches what we've seen before, one with the heating that we've seen. It matches with the measurements of CO2. We know the amount of CO2 has been going up. Here, what we're trying to do is see if we can tease out, and divide this, separate it into different contributing factors, right? Because, we can have whole models on how the population is going to increase, right? If the population were to double, we'd be in deep doo-doo because we're going to need a lot of energy to support a doubled population. Is population going to double over the next 50 years? Probably not. Um, depending on, depending on which country you're talking about, populations in some places are stable and in some places are even going down, whereas in other countries, they're going up. And so we have a lot of different population models. We know population's still going to go up, but we can probably fairly accurately predict how the population is going to change in, say, the next 50 years. We've got some pretty good data and tracking on that. Now, affluence, how much GDP is going to increase over each year. There's a lot of economists that focus entirely on models of GDP per country, per region, per industry. And so we probably have, a fair measure of how affluence is changing. Energy intensity is about choices, right? It's about, or I should say, carbon intensity is about choices. What will we choose to get our energy from? Are we going to use CO2 intensive methods or not? Energy intensity, we've seen, has been coming down, and my guess is will continue to come down. There's always a driver to make things more efficient in the way our economies work, the way businesses work. And so there's always going to be this desire to reduce the energy intensity of all the things that we use and drive and stuff. And so what the IPAT model allows us to do is to separate these contributing factors to emissions. And so we can make some predictions about the future. Now, we've seen how it models the past. And so we can look to see how population and affluence will affect things. And we've seen that in the past 60 years, that increases in both of those were offset a little bit by decreases in the energy intensity and carbon intensity. But now the question really becomes, what are future CO2 levels going to be, right? Because in order to predict future warming, we need to know how much CO2 we're going to produce next year and in the year after that. And that's where folks at the IPCC and in governments all around the world are struggling with, is to figure out, okay, how much are we going to change our emissions? And it's hard to predict, what decisions are going to be made, because a lot of them are political decisions. Here in the US, we had, at least during the Obama administration, a clear and strong pressure to move away from coal-fired plants, to move away from carbon-intensive means of energy production, and to go into more solar and wind power and renewable energy things. Donald Trump is been trying to reverse that for a long time. they've done a number of things in his administration to kind of start to reverse that. And then the Republican plan for whoever becomes president, if they're a Republican in the US, I think it's called the 2025 project, is all about getting rid of all climate controls and actually subsidizing a return to coal-fired plants and oil production, because that's where they get a lot of their, campaign contributions from. So it's anybody's guess what choices we're going to make, but at least we know if we have a model to kind of predict future, then we can know how bad the problem is and what kinds of things we need to do. And later on, when you come up with projects, biotechnology projects to mitigate the effects of climate change or fight climate change, we now have an idea how to calculate the effects of those projects, right? If you were to create a new technology that reduces the carbon footprint, we now have a model to see, well, how actually could that affect the overall big numbers? It's kind of neat. Any questions?
No problem.
Okay, so where is this all leading? Where it's leading is in the next chapter, in chapter 9, we're gonna, well, actually, we're still in chapter 8. So in the next part, we're gonna talk about future warming using these models. And the IPCC has a couple different models based on what choices we might make. Like, if we keep things as they are right now, what does the future look like? If we take a sudden U-turn and get rid of all of our CO2 producing stuff today, what does that look like? And then what are the things in between? And so they have a couple different what we call climate scenarios, depending on what kind of choices countries make and the world makes, and how much do those choices matter at this point, and how much is already baked into the equation? Because we know the CO2 that we've put into the atmosphere today, it's going to take, is a radiative forcing. We know that radiative forcing is going to be amplified by those feedbacks that we talked about. Remember, only about 30% of the warming that we've seen over the last 2 centuries was due to the actual radiative forcing of the greenhouse gases. The other 70% was due to the effects of these feedbacks, right? The ice albedo feedback, the water vapor feedback, etc. Those feedbacks have really amplified those effects. And we know how long, once you put CO2 in the atmosphere, how long it stays there, right? How many years it takes to take some of that CO2 and dissolve it into the mix layer, and then how long it takes for the mix layer to kind of empty out into the bulk ocean, so there's more room for stuff in the mix layer. And we also know how long it takes to mix it with the rocks. And so we know that if we put CO2 in the atmosphere now, a lot of it's going to be there in 100 years. And after 1,000 years, it will still be about 15% of what you put in there, actually about 10,000 years. And we went through that in an earlier section. Anyways, that's where we are. Yes.
Please, I'm concerned about the IPAT relationship with the equation. I'm just wondering, is there going to be an equipment that you're going to be able to measure the amount of the CO2 that is emitted by a person, and in order to be able to charge how much is it per dollar?
Well, by breaking it out this way, we really, for looking at, so GDP is an aggregate number. We can measure it for a country, how much gross product, domestic products, so how much goods and services are produced. And we can divide that by the number of people, assuming people are using that. Again, that's that affluence term. How much GDP does each person use? And by using that bulk measurement, we don't have to measure how much each person used individually. We could, and then multiply it together by all of the people, but then our units would be different. It would be CO2 emitted per person times the number of people, and then you wouldn't need all the rest of this, right? But calculating the CO2 per person is actually really hard when most of the CO2 that you're responsible for was burned by somebody else somewhere else to make the energy for the electricity that you're consuming, right? Now, you could get fine-grained and say, well, I use this amount of electricity, it's produced this amount of CO2, I burn these things. So you could calculate it up as CO2 per person and then multiply it by the number of people. Or you can look at it in a bulk. How much gross domestic product do we make? How much energy did it take to make that gross domestic product? Those are numbers that are very easy to calculate. We've got a lot of these aggregate numbers. It's a lot harder to microscope individual people all around the globe because we got billions of people. You'd never be able to microscope out how much each person is doing because it's going to be different because different people have different amount of affluence. By using these bulk numbers, dollars of GDP, total amount of energy per GDP, and the CO2 per joule, those are a lot easier to determine and calculate. Certainly we know it's just physics, how much CO2 is emitted per joule. That's chemistry. We can look at a process, like we know how many joules we get out of burning a lump of coal, and we know how much CO2 for that same lump of coal is emitted. So we're good on that aspect. For those of you who have access to the Moodle for the course, in midterm assessments which is where we are now. We've got the video got a couple of things here. We've gone over the Hadley cells. We've done the continental drift. We've just done the IPAT prediction, and I'll upload the video soon. There is a midterm exam to go ahead and try and do. So if you have access to the Moodle, go ahead and do that. I know some folks don't have access to that. Don't worry about that. I'm interested in giving you questions, so you kind of know what kinds of things you need to know, and I'll email those out to you directly. But for everybody else, try and hit this midterm exam by Monday, have it filled out, and I'll get an idea how you do. And I'm not going to say don't use your notes or anything like that, because that's almost impossible to manage when you're doing an online class, which is why I don't put a lot of points into things like this. Just do your best and see what you know and give me an idea of what you know. Thanks, everybody. Have a great day. Have a great weekend.
Thank you, Prof.
Okay.
Great weekend.
Talk to you soon. Bye-bye.